This semester we've been spending a lot of time integrating and computing antiderivatives, and examples of the types of problems we might be focusing on would be something like dy dt, the derivative equals t squared plus t to the third, and if we wanted to figure out what y of t is, we could simply compute the antiderivative, which would be 1/3 t squared plus 1/4 t to the fourth plus a constant. Of course, we could also rewrite this by saying simply compute the indefinite integral of t squared plus t to the third. If we had a function whose derivative we knew to be 1 over t squared plus 1, we could anti-differentiate, and we'd know that y of t is simply the arctangent of t plus c. And we can check both of these answers by computing the derivative. Now, in these examples, t is the independent or the input variable, and y is the dependent or the output variable. Differential equations, which form the basis of Chapter 11, are a little bit different. Instead of the derivative being a function of just t, the input, it's a function of the output as well, a function of y. So notice the difference between these two situations. The right-hand side in both of these examples depends only upon t, whereas here the right-hand sides depend upon y itself. Differential equations arise in a variety of contexts in physics, biology, and economics, and if we're given a formula, like one of the above, our goal is to be able to solve it by perhaps finding a formula or a graphical representation or a table. So again, what's important to notice is that the derivative of y is equal to a function not only of t, but also of y itself. Again, the right-hand side here is a function of t and y. Here's a t right here. Whereas what we've been focusing on up to this point, the right-hand side would simply be a function of t. So let's take a look at a couple examples. dy dt equals y of t. In words, this is saying, do we know of a function whose derivative equals the original function? Function whose derivative equals the original function, or a function whose rate of change is equal to the original function. Well, we learned in Calculus 1 that the derivative of the exponential is the exponential itself, or more generally, if we take any constant times the exponential, it would have a derivative which is c e to the t. So the derivative of this function equals the original function. Let's take a look at a slightly different example. dy dt equals k times y of t. In words, this is saying that the derivative of y with respect to t is directly proportional to y of t. K is a constant of proportionality. Now later in this chapter we'll show how to get a solution to this. Y of t equals an arbitrary constant times e to the kt. For now, we're simply going to be focusing on checking solutions. So the way we can check a solution is we can plug it into both sides of an equation and verify that the two quantities are equal. So let me plug this into the left side of the equation. That means I need to take the derivative of this quantity with respect to t. And if I take the derivative of this quantity, I get c e to the kt times k using the chain rule. On the other hand, if I look at the right-hand side and simply take y and multiply it by k, I get kc e to the kt. And because the result of plugging this into the left side and the right side is the same, I've verified that this is a solution. Here's another example. dy dt equals y of t plus 10. In other words, the rate of change of y is equal to y plus 10. We'll show later that a solution to this equation is the form minus 10 plus an arbitrary constant e to the t. We'll show that later, but let's just verify that this is a solution by plugging it in to both sides. If I take the derivative of this, I get the derivative of negative 10, which is 0, and then the derivative of c e to the t is simply c e to the t. On the other hand, if I plug this solution into the right-hand side, I get minus 10 plus y of t, which is c e to the t as well. And because plugging this into the right side and the left side yields the same result, I know that I have a solution to the differential equation. Another example, the second derivative of y with respect to t plus 4 times y of t is 0. This is what we call a second order differential equation because the highest order, highest derivative is the second derivative. Now, the solution to this differential equation is y of t equals cosine of 2t. Don't worry about how I got that solution, but let's just check and make sure that it's valid. First, the derivative of y would be minus the sine of 2t times 2. That's following from the chain rule. If I take the second derivative, that means I take the derivative of this, I get minus cosine of 2t times the 2 that was here, but times another t by the chain rule. So, if I take this function, y of t equals cosine of 2t, and if I compute its second derivative, I get minus cosine of 2t times 4. If I plug that in here, and if I add 4 times the cosine of 2t, I get minus cosine of 2t times 4 plus 4 times cosine of 2t, and that is 0. So that says that this function is a solution of that differential equation. Now, differential equations have a variety of applications, and let's consider one of the most simplest. Plavix is a medication used to prevent coronary artery disease. Like most drugs, the amount of a single dose remaining in a person's bloodstream decays exponentially. In calculus terms, or in differential equations terms, this can be stated by saying the rate of change of the amount of drug present is directly proportional to how much is present. So we'll assume that a person consumes a 75 milligram dose. This is typical, and we want to find the amount remaining in his or her bloodstream as a function of time. Now, the key sentence here is the rate of change of amount. Rate of change means derivative. So if y of t denotes the amount, then the rate of change of the amount would be dy dt. And that is directly proportional to, or equals a constant, times the amount present, which is y of t. And this constant of proportionality k is an absorption rate. It would depend upon the individual's body in terms of how it absorbed the drug from the bloodstream. We also know that at time 0 there are initially 75 milligrams because that's the dosage, and we call that the initial value. Now, a couple of pages ago we showed that the solution to this differential equation took the form of a constant, an arbitrary constant times e to the kt. We can figure out what this constant c is by using the initial value. If we plug 0 in for t, we get 75 according to the initial value. But if I plug 0 in for t here, I get c e to the 0, which is just c times 1. That means that c is 75, or the solution is y of t equals 75 e to the kt. K is the constant proportionality, but we can actually compute its value. For Plavix, the half-life is about 6 hours, and this is a value that you can easily get just by Googling Plavix and half-life, and we can use this to determine the constant of proportionality. A half-life means how long it takes for a dose to decrease by half. So if I have a 75 milligram dose, and if it decays to half its amount, 32.5, I know that that's e to the k times 6. What I'm doing is I'm using this formula. I'm replacing the time with 6 hours, and I know that after 6 hours there should be 32.5 milligrams remaining. Now let's solve this for k. If I divide by 75, I get 1/2 on the left side equals e to the 6k, or in other words, the natural log of 1/2 is 6k, or k is 1/6 the natural log of a half, which is about minus 0.12. That means that the solution to the entire problem is y of t equals 75 e to the minus 0.12t. And if we graph that, we get exponential decay, which is what we would expect. Here's another example. It's known as Newton's law of cooling. Newton's law of cooling states that when an object of a certain temperature is placed in a surrounding of different temperature, the object's temperature rate of change is proportional to the temperature difference between the surroundings and the object's temperature. And this is really restating the obvious. If we have a hot cup of coffee and we know it's going to cool to room temperature, in this case we're going to look at a frozen pizza. We'll assume that it's 20 degrees Fahrenheit and we're going to put it into a 400-degree oven. We'll let F of t denote the temperature's pizza after t minutes in degrees Fahrenheit. So in words, we know that the object's temperature rate of change, that means the derivative, the rate of temperature change, is proportional to, equals k times, the difference between the surroundings temperature and the object's temperature. And the difference would be 400, that's the surrounding, that's the oven, minus y of t, which is the temperature. So here we have a differential equation, and I can see that I've made a mistake. This should be capital F of t, and this should be capital F over here. At time 0, the temperature is 20 degrees Fahrenheit. Now, we will show later on that the solution to this differential equation is F of t equals 400 plus c e to the minus kt. C is an arbitrary constant. K is a proportionality constant that depends upon our oven. But C is an arbitrary constant. And we can determine the value of C by using this initial temperature. Let's plug 0 into this formula. If we plug 0 into this formula, we get 400 plus C times e to the 0. And we know that has to equal the initial temperature of 20. So 400 plus C equals 20, or in other words, C equals minus 380. So that means our solution is y of t equals 400 minus 380 e to the minus kt. And notice what happens as t gets large. This exponential is going to go to 0, which means this whole quantity will go to 0, which means the temperature will go to about 400 degrees. In other words, if we leave the pizza in the oven long enough, its temperature will rise to 400 degrees, which is somewhat obvious. So here are some problems for you to work on in preparation for class. Verify that the function y of t equals 3 sine 4 of t plus 2 cosine 4 of t is a solution to this differential equation. That means you want to take the second derivative of this expression. You want to plug it in, and you want to show that when you take minus 16 times this expression, you get the same thing. Verify that y of t equals e to the 2t plus e to the minus 2t is a solution of the second derivative of y equals 4 times y. So again, you want to take the second derivative of this, plug it in. That would be the result here. Takes 4 times y of t and show that the results are equal. And lastly, verify that y of t equals 10 plus 3 e to the minus 4t is a solution of dy dt equals 4 times 10 minus y of t. So take the derivative of this, and then take 10 minus this, and show that they are, in fact, the same thing. And so what you'll be doing is you'll be creating diagrams that are very similar to what we did earlier. So do this in preparation for the next class. See you then.